Morning, my name is Mrs. Chiverton and I'm one of the science directors, and I'm going to be taking you through a series of lessons on the C3 unit about quantitative chemistry. For today's session, before we start, can you make sure that any notifications are switched off on the device that you are listening and any other devices around you? Can you also make sure you've got some paper or your exercise book and a pen, pencil and ruler in order to complete these? You're also, for this section, going to need access to a calculator. If you don't have your calculator at home with you, then you usually will find a calculator app on a phone and on any computer devices, and you can always pause the video in order to use the calculator. For this section, you will also need your planner, and if you turn to page 147 in your planner, you will find a periodic table, and you are going to need that to look up the atomic masses of some of the substances as we go through this unit. Okay, to get our brains working today, what we're going to do is practice balancing some simple equations. You've done this before. Remember, we count up the types and amount of atoms on the left-hand side of the equation. That's the reactants, and that has to equal the same elements, the same formula, and quantities of those formula on the right-hand side in the product. So I'm going to give you a minute and 30 seconds to try and balance these three equations. The equations are increasing in difficulty. So 1 minute 30. Okay, hopefully you've had a chance to balance those and you've used the methods that we've shown you before of counting up the different atoms on both sides of the equation. So, check your answers. So, moving forward, this is the fourth lesson in the quantitative chemistry series, and in this one we are going to be calculating reacting masses. So that's your title for today's lesson, so please put that into your exercise book or on your paper, calculating reacting masses. Make sure you've underlined your title and you've put a date on so you know what order you've done these activities in. So in today's lesson, our challenge is to be able to use balanced simple equations to calculate the number of moles and the mass of a reactant or a product. And our aspire is to be able to explain how to use the mass of reacting substances to work out the balancing numbers in an equation. Now this activity is for students doing higher tier only. So if you are doing foundation tier, you do not need to complete these activities. Sometimes it's useful to know how much of a compound is made up of a particular element. Now this is known as the percentage composition by mass. And there's a complicated equation, or it seems complicated at first view, to actually allow us to do that. Z just represents the element that you are trying to find out about. So to work out the percentage of that element in a compound, we need to know the number of atoms of that element in the compound, the atomic mass of that element, and the formula mass of the whole compound. So the number of atoms of the compound we will get from the formula, The atomic mass we can look up in our periodic table, and we will need to calculate our formula mass of that particular compound in the method that we've used previously. So that's the element we need to know about. That's what we will get from our chemical formula. That we would get from our periodic table. And this we may need to work out, or it sometimes is given to us as part of the question. So here's an example. If you were asked to work out the percentage of oxygen in carbon dioxide, we would look up our atomic masses, and we've got the masses of carbon and oxygen there. So the formula for carbon dioxide, of course, is CO2. So that tells us, because of that little number 2, that there are 2 oxygen atoms in every molecule of carbon dioxide. The atomic mass of oxygen is 16, and the formula mass for the carbon dioxide is our 12 plus 2 lots of 16, which comes out as 44. We then need to put these numbers into the equation that I've given you above. So for the percentage of oxygen, we need the number of atoms of oxygen, which is 2. We need the atomic mass of oxygen, which is 16. So we multiply those two numbers together. We then divide it by the formula mass of the whole compound, which was 44. And then because we want it as a percentage, we multiply it by 100. And that should give us an answer of 72.7%. So 72.7% of the mass of any molecule of carbon dioxide is made up of the mass of the oxygen atoms. Okay, so for this one, we are going to use that formula, and we're going to calculate the percentage of oxygen in the following compounds. And you need to show all your working out. Now, if you want to challenge yourself and come up with the formula yourself, work from this slide. If you need a little bit more help with the formula, then on the next slide, the formula for each of those compounds is given. So remember, when we're calculating, we're working out a number. You are expected to use your calculator, so don't do any mental maths, because there's a chance that you might make a mistake, and you must show all of your working out. So I will set the timer going on here. As I said, if you wish for some extra help, you can fast forward onto the next slide, and that will give you a little bit of a helping hand with the formula of the various compounds. So for those of you who are struggling a little bit with working out the formula for these compounds, there are the formula on the left hand side: MgO, K2O, NaOH and SO2. So if you have skipped to this stage, then you can pause the video and give yourself 2 minutes to work out the mass of these. If you are already done that, then I'm going to work through the process with you. So magnesium oxide, you can clearly see, has 1 oxygen atom there, and that gives it a mass of 16. The formula mass is of course 24 plus 16, which makes 40. So if we plug those numbers into our formula, we find that we have 16, because there's one atom of oxygen, divided by 40, which is the formula mass, and then we multiply the whole thing by 100, and that comes out as 40%. For K2O, the mass of a single oxygen atom is still 16, but in our formula mass we have got 2 potassium. 2 times 39 plus 16 makes 94. So in this situation again, we do 16 divided by the 94, multiplied by 100, and that gives us our 17%. For sodium hydroxide, again, the mass of the oxygen is 16. We've only got one atom of oxygen. So again, when we work out our formula mass, we simply add the three numbers together. 23 plus 16 plus 1 makes 40. So again, it's 16 divided by 40, multiplied by 100, and we come out as 40%. So 40% of the mass of every sodium hydroxide molecule is made of oxygen. The final one, we have got 2 oxygen atoms there. The mass of an oxygen atom is still 16, and the formula mass will be 32 plus 2 lots of 16, making a total of 64. But when we get to our calculation for the percentage of oxygen, we need to have the fact that it's 2 lots of 16, 2 atoms of oxygen, multiplied by the mass of the oxygen. We divide that by the formula mass of the compound, the 64, and then multiply it by 100, and it comes out as 50%. So hopefully you got all of those answers correct. Now, this is a typical exam question that is based on this. And actually, it's broken very nicely into separate sections for you. You first of all have to calculate the relative formula mass of something called tin fluoride. You've then got to calculate the percentage by mass of fluorine in the tin fluoride. And then the next step is to calculate the mass of fluorine in a tube of toothpaste when they tell you the amount of tin fluoride that is actually in there. Okay, so I'm going to give you 4 minutes to work through this series of calculations. It's not as tricky as you think if you work through using the methods that we've met so far. Okay, hopefully that's been enough time to work your way through this question. And it is nice that they've split it up into sections. So we can work at the first one, the relative formula mass of tin fluoride. And they've actually given you the atomic masses there. So what we should have for that one, when we're calculating it, we need to look at what we're doing and we need to think in each case about what every step is going to be and what we're being asked to do. So for that first one, your answer should have been 157. We have got our tin, which is 119, and we have got 2 atoms of fluorine, so which is 19 each, so we should have got 157. If you only got 158 because you only added one of the fluorine molecules, then you get 1 mark for that section. But we then need to use that to calculate the percentage by mass. So you should have got an answer of 24.2. So again, when we're looking at this, you should have realised that there was 2 fluorine atoms at 19 each, and then we divide that by that atomic mass that we've just worked out, the 157, and multiply it by 100. Okay, and that should have given us our 2 marks. Now again, if you had made a mistake in the original one, but then you had clearly used that in the formula, you could still get 2 marks. If you forgot to multiply your fluorine atoms by 2 in this one, then you would have only got 1 mark. Your answer would have come out as 12 or 12.1. So just check that and make any amendments that you do. Now, this part is the bit that usually does confuse people. It tells you that a tube of toothpaste contains 1.2 grams of tin fluoride and asks you the mass of fluorine in the tube of toothpaste. It's obvious because it's the third part of the question that you are likely to need your answers from the previous section. So the answer should have been 0.29. Now we would accept any answers between 0.28 and 0.3. Okay, so you should have had your answer divided by 100 and then multiplied by the 1.2 in order to get that. So in this situation, obviously we had that 24.2 divided by 100 multiplied by 1.2, and that's where we get our 0.29 from. So hopefully you managed to get 6 out of 6 on that. So now we're going to go on and look in more detail about how we can use moles. So we're looking at advanced mole mastery of using the mole. And as it says there, it's about to get serious. In reality, so long as you follow through in the series of calculations that we do, following every steps and showing you're working out, you should get full marks. And even if you don't get full marks, you should be able to pick up working out marks as you go along. So if we looked at this and we wanted to balance this equation, magnesium plus hydrochloric acid makes magnesium chloride plus hydrogen, what we would need to do is count up the relevant number of atoms on each side, and a simple number 2 in front of the hydrochloric acid would balance that equation. That gives us the 2 hydrogen atoms and the 2 chlorine atoms that are needed on the right hand side of the equation. But what do these numbers actually mean? It's all to do with proportions and ratios. What they are is effectively the number of moles that will react with each other. So what this equation tells a chemist is that 1 mole of magnesium will react with 2 moles of hydrochloric acid to produce 1 mole of magnesium chloride and 1 mole of hydrogen. And if we increase the moles of any one of those, it will increase the other moles by the same proportion. So first of all, you're going to practice balancing equations because this comes up time and time again on every exam paper. And then you're going to identify how many moles there are of each substance in our balanced equations. And I'm going to give you 3 minutes to have a go at this activity. You're just doing exactly the same process as I did in our example there. Okay, so let's have a look at the answers to this one. You can mark these as we go through. So you should have balanced out that we needed 2 magnesium atoms for every 1 molecule of oxygen and it will make 2 molecules of magnesium oxide. So in terms of our moles, 2 moles of magnesium plus 1 mole of oxygen produces 2 moles of magnesium oxide. We're just looking at those big balancing numbers. With sulfuric acid and sodium, 1 molecule of sulfuric acid with 2 moles of sodium produces 1 mole of sodium sulfate and 1 mole of hydrogen. Again, just looking at those balancing numbers. And finally, with our calcium carbonate, it was already balanced, so that tells us 1 mole of calcium carbonate produces 1 mole of calcium oxide and 1 mole of carbon dioxide. So let's just remember and recall from a previous lesson what is meant by the conservation of mass. I'll give you 1 minute to write down the definition of conservation of mass. Okay, so what you should have said is that no mass is gained and no mass is lost during a reaction. Mass is conserved. So the total mass before a reaction is equal to the total mass after a reaction. In other words, the total mass of the reactants is equal to the total mass of the products. And hopefully you managed to recall that without too much difficulty. So when we look at molar ratios, the ratios of the reactants and the products does not change in a balanced equation. So for example, this very simple equation shows that nitrogen will react with hydrogen and produce a gas called ammonia. So 1 nitrogen molecule reacts with 3 hydrogen molecules and will produce 2 ammonia molecules. If we had 12 nitrogen molecules, then we would simply times the number of hydrogen molecules also by 12, so that would give us 36, and we times the number of ammonia molecules by 12, which would give us 24. That would be a dozen, 3 dozen, and 2 dozen. We are keeping the ratios the same every time. So whatever we do to one of the molecules, we have to do the same to the other. Okay, so 6 times 10 to the power of 23 molecules of that would need 18 times 10 to the power of 23 molecules of that one, and 12 times 10 to the power of 23 molecules of that one. In other words, 1 mole, 3 moles, 2 moles. We are keeping the ratios the same. So whatever we do to one, we have to do the same to the others. So here's an example for you to look at. We have got 1 mole of propane. I know it's 1 mole because there's no number to balance it. It would need 5 moles of oxygen to react with it, and it would produce 3 moles of carbon dioxide and 4 moles of water. So what I want you to do is to predict how many moles of the oxygen, carbon dioxide and water would be needed if we started off with 10 moles of propane, 2 moles of propane, 0.5 moles of propane, or 3 moles of propane. Remember, you need to keep the molar ratios the same in each case. I'm just going to give you 1 minute to actually work through this, if I can get the timer to work. Okay, let's check your answers again. Amend them if you have got any wrong. So if we have 10 moles of propane, we simply times the 5 by 10 as well. That would be 50 moles of oxygen. It would produce 30 moles of carbon dioxide and 40 moles of water. If we have got 2 moles of propane, we would need 10 moles of oxygen. So all we're doing is whatever we've done, we have to do it to the same to the others. So if we've doubled the moles of propane, we have to double the moles of oxygen and double the moles of carbon dioxide, which would give us 6, and double the moles of water, which would give us 8. If we've halved it, we do the same. We halve the quantities each time. If we've times it by 3, we times all of the other quantities also by 3. So what we are doing is we are keeping the molar ratios the same according to the balanced equation. Well done if you got all of those correct. So we can then use this principle to actually calculate the mass of something, such as the carbon dioxide produced, if you only know the mass of one of the reactants. So what we can do here is we use the moles to calculate the mass of the reactions or products within that reaction using our favourite equation, mass equals mR times moles. The logical steps when we're looking for the reacting mass calculations. We start off by writing down what we do know about the masses and working out the relative formula mass of any of the relevant chemicals. We then need to find out the moles of the chemical that you do know the mass of, using moles equals mass divided by the molecular mass. We then use the molar ratio to find the number of moles of the chemicals that we don't know anything about yet, and we use the balanced equation in order to do that. And then finally, we find the mass of that chemical that we've been asked about in the question using mass equals moles times mR. So let's work through an example together. If we've got 24 grams of carbon, how much carbon dioxide will we make? We start off with our balanced equation, C plus O2 turns into CO2. So we can do it in the form of a table. We write down the 3 quantities that we need to work out, mass, formula mass and moles. We write down the 2 chemicals that are relevant, the carbon and the carbon dioxide. And then we fill in anything that we already know. So for example, we know that there's 24 grams of carbon. We can fill in formula masses. So for example, carbon, it's the atomic mass, which is 12. And for carbon dioxide, we can work out that it's 12 plus 16, which gives us a formula mass of 44. So at that point, we've put in everything we do already know, and now we need to start doing some calculations. So first of all, we're going to work out the number of moles of carbon, and we do that by remembering mass equals mR times mole. So we substitute into our equation the numbers that we do know, and we end up with 24 divided by 12 gives us 2 moles of carbon. So 24 grams is 2 moles of carbon. We then look back at our equation and we look for the ratio. Now, there are no balancing numbers in our equation, so we know that it's a 1-to-1 ratio. So if we have 2 moles of carbon, that will mean we also have 2 moles of carbon dioxide. We can then go back to our mass equals Mr. Mole equation, and we have the formula mass, the mR, we have the number of moles, 2, so we substitute those back into the equation, and we get 2 times 44 would be 88 grams. So 24 grams of carbon reacting with oxygen would produce 88 grams. So I'd like you to try the next two questions using that same method of using a grid. So remember, work out what you already do know, work out the formula masses of the relevant compounds or elements in the question, work out the number of moles, use the molar ratio to work out the moles of the one that you don't know, and then mass equals Mr. Mole to convert that into a mass. Now, as it's quite a few stages in the calculation, I'm going to give you 4 minutes to answer both of these questions. Remember, please show all your working out nice and clearly. 4 minutes, off you go. Okay, change your pen and we will go through and look at how we can actually answer these. So, don't forget to make sure that your equations were balanced. first. So our first one, 20 grams of calcium, how much calcium chloride would we make? So in this case, the equation is balanced. So we're writing in what we do know, which is 20 grams of calcium, the formula mass of which is its atomic mass 40. And for calcium chloride, we can work out that the formula mass is 111. We go back to mass equals Mr. Moles to work out that the number of moles is 20 over 40, which comes as 0.5 moles of calcium chloride. Again, looking at the balanced equation for the molar ratio, it's a 1-to-1 ratio, so there's also 0.5 moles of calcium chloride. We then substitute those two numbers back into our equation. 0.5 times 111 comes out as 55 grams of calcium chloride. Hope you got that one correct. Our second one was about iron oxide reacting with carbon monoxide. So again, in this case, we have got 100 tonnes of our iron oxide. We have got a formula mass of 160, and for the iron, the atomic mass is 56. The number of moles, we're just going to ignore the tonnes for now, and we're going to say that it is 100 divided by 160, and it comes out as 0.625 moles. It's a little bit of a cheat this, but it works. We then look at our balanced equation and we see it's a 1-to-2 ratio. So therefore we need to double the number of moles of iron that are produced. So in this case, it's the 0.625 times by 2 comes out as 1.25 moles. We then substitute our numbers back into our equation again to work out the mass of iron produced. Now it comes out as 1.25 times 56 equals 70. And then we can add our tonnes back in and our answer should be 70 tonnes. Again, hopefully you've managed to get those. If you didn't, go back a few minutes in the video, look back at my worked example and see if you can have another go. So this is a typical exam question based on this. I've actually cheated and squeezed up the amount of space that you would have to calculate each of these so that you can see it all on one screen on the video. So make sure you do leave yourself plenty of space to work out the information. I'm going to give you 3 minutes in order to actually calculate this. So limestone, CaCO3, is a raw material. On strong heating, it's converted to calcium oxide, which is a useful substance. And we have the equation there, and it's a balanced equation. So the first easy 2 marks is simply to work out the molecular mass of your calcium carbonate. And then it tells you that about 60 million tonnes of calcium oxide is made in Britain each year. And it's asking you to calculate the mass of calcium carbonate needed to make this amount of calcium oxide. Now remember what I did in our previous example where I ignored the million tonnes bit and just went ahead with my simple calculation and then added that back in at the last minute. So if the timer will play ball, 3 minutes, off you go. Okay, so let's see how well you have done. We've got our values in there, and we must remember that we should have used our calculator and shown our working out. So the first stage was easy. It was simply working out the molecular mass of the calcium carbonate. So we had 40 plus 12 plus 3 lots of 16 for the oxygens, and it came out as 100. And you needed to show your working out clearly in order to get both parts of the marks. The second part of it, the answer should have come out as 107.1 million tonnes. And it's broken down into 4 marks, 1 for the molecular mass of the calcium carbonate, 2 for showing how we actually work out that mass, and the third one for the actual final answer. Now we can do that by our table method again. So we know that it was 60 million tonnes of calcium oxide. We know the formula mass for calcium oxide is 56. So the number of moles, we do 60 divided by 56 comes out as 1.071. We know from the balanced equation that it was a 1-to-1 ratio. So that means it's the same number of moles of the calcium carbonate. We use the molecular mass of calcium carbonate, which we've previously calculated. This is where it's really important to show your working out, because if you get that wrong initially, but you've used this method using your wrong formula mass, you can still get all of the marks for this section, which is worth 4, of course. And then we finally substitute that back into our mass equals mR times moles equation. So it's 100 for our formula mass multiplied by the number of moles, and it comes out as 107.1 million tonnes. So hopefully you managed to get to that answer as well. So we've been able to use balanced symbol equations to calculate the number of moles and mass of a reactant or product. Now we're going to look at being able to explain how to use it to work out the balancing numbers in an equation. So what are we going to do if it happens in reverse? Can we use those masses of substances to work out the balanced equation? And of course the answer is yes. We still have to use our same equation, mass equals mR times mole. So when we're balancing equations, we look at what information we've already got. So in this situation, 22.4 grams of iron reacts with 9.6 grams of oxygen to form iron oxide. Using our idea of conservation of mass, we can work out that this would produce 3.2 grams of iron oxide. We've simply added the masses of the reactants and it will equal the mass of the products. So that is our conservation of mass. And then we need to look at what the balancing numbers of the simple equation would be. And again, it's a simple, straightforward process if you work methodically. You would be given the formula masses of the substances involved. So in this case, iron is 56, oxygen is 32, and the iron oxide is 160. So we start off with our word equation and we look at what masses each of those have. So we've put those masses in. We know what the molecular masses are, so in order to find the number of moles, we simply divide the masses by the molecular masses, and that gives us the number of moles. And in this occasion, we have 0.4 moles of iron, 0.3 moles of oxygen, and 0.2 moles of iron oxide. And remember, those ratios never change. So if we look at the overall ratio and convert that to whole numbers, we have a 4 to 3 to 2 ratio. The ratios stay the same. We've times all of them by 10. So therefore, these are the balancing numbers that we need in our equation. And what we end up with is 4 moles of iron reacting with 3 moles of oxygen to produce 2 moles of iron oxide. And if we follow this pattern every time, you should always get full marks on these questions. So what I'm going to do now is give you a challenge. This is a little bit more tricky than the basic one that I've done, but it's the same principle and the same working out. So 2.2 grams of a hydrocarbon is burnt in oxygen and produces 3.6 grams of water and 6.6 grams of carbon dioxide. What would the balancing numbers of the simple equation be? And I've given you, again there, the formula masses of any compounds that you need to balance this equation. What I'm going to do is I am going to give you 2 minutes to work through and come up with the balancing numbers for the simple equation. So remember, write out the word equation first and put in the values for the masses that you know, and using conservation of mass, work out the mass of the substance you don't know. Then use the formula masses and mass equals Mr. Mole to work out the number of moles of each chemical, and that should give you your molar ratio, which will allow you to come up with your balancing numbers. If you haven't quite finished and you need some more time, just pause the video and take your time working this out. But now we'll go through the answers together. So first of all, there's our word equation. Hydrocarbon plus oxygen turns into water and carbon dioxide. We know the masses of the hydrocarbon, the water and the carbon dioxide, and because of conservation of mass, we can work out that the mass of the oxygen should be 8 grams. We can write down the molecular masses of the chemicals as we know them, and then we simply work out the moles by dividing the masses by their formula masses. And what we should end up with there is 0.05, 0.25, 0.2 and 0.15. Now we want those converted into whole numbers, so therefore our ratio is a 1 to 5 to 4 to 3 ratio. And those are the numbers that we would need to balance our equation. So once we've got that, we should be able to write a balanced symbol equation for the reaction, but we need to work out the formula of the hydrocarbon first. So that's our balanced equation, not knowing what the hydrocarbon looks like. We simply put in those balancing numbers in front of the chemicals that we do know the formulas for. And then by looking at our conservation of mass and our conservation of atoms to balance those equations, we count up how many atoms of each one there are on each side. So currently, with that balanced equation, but nothing in front of the hydrocarbon, so we know there's only one molecule of that, we know that there are 10 oxygen atoms on the left in the reactants, and if we add them up, we've got 4 plus 3 times 2 is 6. We've got 10 oxygen atoms there. So that's great. That's balanced. We know that on the product side, we have got 3 carbon atoms and we have got 4 times 2, which makes 8 hydrogen atoms. So if we've got those in the reactants, in the products, and it's a balanced equation, we must also have them in our reactants. So that should also be 3 and 8. So therefore, we now go back to our hydrocarbon. We know it's hydrogen atoms and carbon atoms, so it becomes C3H8. So I hope you managed to get that as well, working through that process. So that means we have now met our Aspire learning outcome. And this is another similar exam style question. So it says a student placed a conical flask containing 1 gram of a group 1 carbonate. So M is an imaginary element from group 1. We don't know what it is. It could be sodium, it could be lithium, it could be potassium. He added 50 centimetres cubed of an excess of dilute hydrochloric acid to the flask and measured the mass of carbon dioxide given off. We have got the balanced symbol equation there with M representing an unknown element from group 1. And it asks us to calculate the amount in moles of carbon dioxide in 0.32 grams of carbon dioxide. So our second part to the question is how many moles of the metal carbonate are needed to make this number of moles of carbon dioxide. And I'm going to give you just a minute and a half to work through that. Remember, mass equals Mr. Moles, and all the time we're just working backwards and forwards between these things. Okay, so let's see what you've done. The first one is really straightforward. We should know that the mass equals the formula mass times by the moles. So we had a mass of 0.32 from the question. The formula mass, we could work out that it was 12 plus 3 lots of 16. And then we multiply that by the number of moles. So that's 0.32 divided by 44, and it comes out as 0.007272727272. Now, at that point, I would not round that because we're going to need that later on. But how many moles of the metal carbonate are needed to make this number of moles of carbon dioxide? We look back at our balanced equation and we realise that it's a 1-to-1 ratio. So therefore, it's exactly the same number of moles of the metal carbonate. Now what happens is the question then continues and it says the mass of the metal carbonate was 1 gram, and it asks you to use that information and your answer to C part 2 to calculate the relative formula mass of the metal carbonate. And if you hadn't got the correct answer or you hadn't been able to work it out, they give you an answer to use. But as we've worked ours out, you should be able to do that. And then there's a final part to the answer where we should actually be able to work out what the relative atomic mass of the metal is and then use our periodic table in order to actually identify the metal. So this is a real challenge. We are up in the grade sort of 7 and above category, but I'm confident you can have a go at this. So 2 minutes to work your way through. Okay, so hopefully you've worked your way through those. As I said, often there's a lot of information that gets quite scary, but in reality, it's not as scary as it may seem. So, first of all, when we look at this one, we're back to mass equals mR times moles. We substitute in what we do know. So we know from the question it was 1 gram. We know the number of moles from our previous answer was our 0.0072727. Okay, we simply rearrange that to solve for finding the MR. And we should have found out that the MR comes out as 138 for the metal carbonate. We then, knowing that that is the case, we work out what the atomic mass of that N2 is. So we know the total is 138. We take off the atomic masses of the atoms that we do know. So a carbon is worth 12, and there are 3 lots of 16 for our oxygens. So the mass of 2 of the atoms of the metal comes out as 78. We divide by 2 to find the mass of 1 atom of that metal, which comes out as 39. If we look up the element in group 1 with an atomic mass of 39, then the element is potassium. Well done if you managed to work your way through that. And hopefully you will see that even though the questions sound complicated and do involve a lot of staged processes, it's still always working on those same principles of mass equals mR times mole, and that molar ratios in balanced equations do not change. And there's the final answers there as it would seem on the exam papers mark schemes. So there are lots of opportunities to pick up marks even if you've made an error early on, but only if you've shown all of your working out and in a logical manner. So these are the key points from the lesson. We've got that equation for working out the percentage by mass of an element. We've got our information about working out molar ratios and what that actually means. And we have got the process for finding out about reacting masses. And we know that we just reverse that if we're working in the opposite direction. So please look at the notes you've made this lesson. And if you haven't got any of that information down, pause the video and add those pieces of information to your book. And then finally, there is another Google quiz in order for you to test out your knowledge again. So the quiz will be automatically marked, and you will get some instant feedback on that. Good luck with the quiz, and I'll see you in our next quantitative chemistry lesson.